Section 4.4 is on page 276, and this is a very important section. It talks about logarithmic functions. The definition of a log using algebra says if a is bigger than 0 and a not equal to 1, then log base a of x equal y means x equal a to the y. The domain of a log base a of x has to be strictly bigger than 0. Log base 10 of x, we just say log, but this is really what you want to pay attention to. This is what we're going to use all throughout. If you see a log with a base of e of x, we simply say that's a natural log of x, and that's a key on your calculator. Now we're going to start off with 3 properties of logs, very important to know. If you take the log of any base of 1, that's always 0. Log of any base of 1, that is 0. We're going to stick with exponentials. Now, those two we're going to use to solve equations. If you take a log base e and the argument, that's called the argument, happen to be an exponential, they undo each other. And similarly, if you take an exponential function and the power happen to be a log in which those two match, they undo each other. We're going to use that to our advantage, and we're going to start off with the very first set of problems, which says write the logarithmic equation as an exponential and vice versa. So to solve, when I see a log, I need to go to exponential, and when I see an exponential, I need to go to log. So the way it works, if I have the log on one side, everything else on the other side, or if I have the exponential on one side, everything else on the other side, then I could proceed and use this trick. The trick is, if I have a log and I want to get rid of that, I'm going to make both sides power. And the base is going to be the same base as that log. In this case, we're going to make it an e. This will only work if I have a single log on one side, everything else on the other side. And based on what I've just shown you, right there, that will simply be 9 equal e to the 2.1972. So this section, this set of problems, is nothing more than you practicing how to go back and forth. If I see a log and I want to get rid of that, there is a way. I make sure that I have a log on one side, everything else on the other side. And if I want to get rid of a log, I'm going to make both sides of the equation a power. You're allowed to do that. You could choose the base to be anything you like. To get rid of the log with base e, we're going to choose any. And in our class, we're going to stick with that all throughout. So that wouldn't really throw you off at all. You could always think of that's what we're going to do, because that is true. And 6 and 8 is going backwards. That is, if I see an exponential and I want to get rid of that, the key is for me to get rid of the exponential function, isolated by itself, that is. Once I get it by itself, I'm going to use this. So once I have an exponential by itself, I have e squared equal 7.3891. I'm going to log both sides. But what base should I use to eliminate an exponential with a base e? The same base. In our case, it's going to always be natural log. So 2 equal natural log of 7.3891. And the reason we want natural log, because you could use a calculator. And the same deal here. We look at this, say, wait a minute. Isolate the exponential by itself, and it's already isolated by itself. Then what I'm going to do, I'm going to log both sides, and it's no big secret what base should I use. We're going to use ln all throughout the course. And there it is. Now, we have 3 properties of logs that we want to play with. For now, let's apply them. Oops. 3 properties we just talked about, and there are 3 laws. So, if I look at this, I notice, wait a minute, this is already a log of an exponential. This is already matching this, so I'm left with a power. What's the power? That is 2x minus 1. Done. So this part, again, is nothing more than us getting used to this. And if I see an exponential, say, wait a minute, that's the base is e, and of a log, they undo each other. I'm left with simply radical x. And that's sufficient. Here, this is negative 8 plus. Those undo each other, and I'm left with an x cubed. So, very important to be able to go back and forth, and you will see why in a couple of minutes. Properties of logs. If x, y, and n are positive, in which x and y are bigger, these are all the conditions to satisfy the definition. Well, if you take natural log of two things multiplied, think of always logs and exponentials are inverses. When you multiply two exponentials, you would add the powers. That's how I memorize those. When you divide exponentials, you subtract the powers. And the most famous of them all, this separates logs from anything else. When you raise powers, you multiply. This is the one property of logs that doesn't exist anywhere else. So we want to play with this a bit, and this is going to help us once we start the calculus pretty soon. So when I look at this, it says use properties of logs to rewrite the expression as a sum difference, right? So 28, this is natural log of 1. Since you are dividing, we subtract, and we know what natural log of 1 is. Isn't that a 0? And how do we know that? It's right there. So my answer would be negative natural log of 5, and that takes care of it. Here, I'm looking at the log. That's natural log. They're multiplied. Wouldn't you say x plus natural log of y plus natural log of z? Here we have a problem. Here, I'm going to write this as natural log. Wouldn't you say that's 5x squared over x plus 3 to the 1/4? By the third property, move that up front. Isn't that 1/4 natural log of 5x squared over x plus 3? Isn't that 1/4 times? Wouldn't that be natural log of, isn't that 5x squared minus natural log of x plus 3 by what property? By property 2. Do you see that? That is 1/4. Can't I say this is natural log of 5 plus natural log of x squared minus natural log of x plus 3? And wouldn't you agree that that's 1/4 natural log of 5? Can't I move that up front? So those are for practice. We really want to get those rules out. We really don't apply those until calculus as heavily. Same deal here. I say, wait a minute, those are multiplied. Wouldn't you say that's natural log of x plus natural log of the cube root of x squared plus 1? Wouldn't that be natural log of x plus natural log? Isn't that x squared plus 1 to the 1/3? And the one special property of log allows you to change powers into multiplication. And that's as far as we can go. And if I look at the last problem, the same deal. So look, that's division. That is natural log of 2x minus natural log of the square root of x squared minus 1. Wouldn't you say that's natural log of 2 plus natural log of x minus? Isn't that x squared minus 1 to the 1/2? Natural log of 2 plus natural log of x minus. I can move that and make it a product. Now, you could leave the answer like that. Most likely the book or the author will take that a step further. I don't expect it to really go that far and say that's natural log of x minus 1 into x plus 1, and say that's natural log of 2 plus natural log of x minus 1/2. And here, since that's multiplication, That's x minus 1 plus natural log of x plus 1. Again, I don't expect you to really go that far. That's good enough. On the next set of problems, solve for x. Again, that's a key for us, something we're going to do pretty soon. So let's deal with this. Let's see how this works. If I see an exponential equation, I want to isolate the exponential equation by itself. But I notice that those undo each other. And that's x squared minus 9 equals 0. X minus 3 into x plus 3 equal to 0. So x will equal a 3 or a negative 3. That had a small trick. It's important to look at those. And if I look at the next problem, I say that's an exponential. I need to isolate the exponential by itself. The exponential is already by itself. So what I'm going to do, I'm going to log both sides, and we're going to use ln, no big secret. Those undo each other. Negative 0.5x is going to equal natural log of 0.075, and x would be natural log of 0.075 divided by negative 0.5. And here, I'm going to use my calculator. And where is it? Here it is. And if I take parentheses ln of 0.075 divided by, one more parentheses. Oh, this calculator has double. Okay, I don't need that. Divided by, again, it's going to be this negative, not this minus, 0.5. I'm getting 5.1805. 5.1805. We always carry a few more decimals. About 3 or 4 will do. This problem I want to solve, well, the same deal. It's an exponential equation. It has an exponential in it. So I need to isolate the exponential by itself. I need to add the 6 first. I need to divide by that to both sides. So I have e to the 3x minus 7. So be careful. The only way this will work if you isolate the exponential by itself or the log by itself. And now I'm going to log both sides. We know how that works. And if I add 7 to both sides, log of 9/2 is a number. You don't need to write the decimals because that's a lot of decimals. You do that at the end. And x would be natural log of 9/2 plus 7 divided all by 3. And you always need to get the approximate. And there's my calculator. And if I take parentheses, natural, yeah, it has it. 9 divided by 2 plus 7, that's the top, divided by 3 for the bottom. And I'm getting 2.83469. 2.83469. And we have a few more to go, and then we're ready for the applications. If I look at this problem, that's an exponential. It doesn't have to be e. This is 2 to the 1 minus x equaling a 6. So what I'm going to do, I'm going to log both sides. What base am I going to use? I'm going to use base e always, no exceptions. By properties of logs, that's what I mentioned was extremely important. I can move this and make it a product. Now, it would be wise if I am to divide both sides by natural log of 6, right? The natural log of 2 both sides because I isolate that, or you could distribute. It really doesn't matter. Whatever you like. Actually, yes, swap those. Excuse me. Natural log of 2 minus natural log of 6 equals natural log of 2 times x. And if I want x by itself, I would divide both sides by natural log of 2. I love it when that happens. I'll divide both sides by natural log of 2. and I would say x will equal, I need to throw this in my calculator, and here's my calculator. I want to take parentheses, natural log of 2 minus natural log of 6, make sure you close parentheses, that's the top, divided by natural log of 2. And I'm getting a negative 1.58496, negative 1.58, I forgot, 496. There it is. And if I look at the next problem, the same deal works. Those are going to be the same, all of them. And all of these are word problems that are coming your way, something you really need to get out of the way. So before I proceed, I need to isolate the exponential by itself. Otherwise, this doesn't work. 1.06 to the t equal 13 over 4. And now that I have the exponential on one side, everything else on the other side, I take the natural log of both sides. Properties of logs. Again, no other function has such a property. And here, it's fairly simple. All what I have to do is divide by natural log of 1.06. And I get t to equal that value. If I throw it in my calculator, I'm looking at parentheses, natural log of 13 divided by 4 all over natural log of 1.06. And I'm getting 20.2279. You could say 785, it really doesn't matter. And one more to go before we tackle our applications. The next problem up, again, a problem that's going to come up for us on the long one. I'm looking at this, and I notice this is an exponential function. Here, this is really, a way of doing this is for me to use my calculator. And let me show you what I mean by that. So if I was to go ahead and store this in my answer, that will save me some writing. So if I take 1 plus 0.06 divided by 12. Now, I know that's stored in my answer. There it is, 1.005. You could write that down if you want. You could say it is 1.005, or you could just use answer. Now what? I'm going to log both sides. What base should I use? We're going to always use base E, no exceptions. I made that a bit too big. And now, we're going to use the properties of logs and move this up front. 12t times natural log of 1.005 equal natural log of 5. To isolate t by itself, I would divide by 12 times natural log of 1.005. Simple algebra, just the logs kind of are in the way until we get used to them. And if I throw this in my calculator, so I have this part 1.005 stored in my calculator. I could plug the whole thing. I could say take natural log of 5 divided by, I keep forgetting it has its own parentheses, 12 times natural log of 1.005, or I could have put answer there, that would have worked, and that will take 2.75 years. 2.75, I'm sorry, it's not a word problem yet. So 2.75 will do.